The blizzard stopped snowing on February 23rd. That's the headline. That's the moment the cameras packed up and the news cycle moved on. But inside the forecast discussions from the National Weather Service, a different story is unfolding, one they're quietly calling historical. 2 to 3 feet of snow are now locked in a brutal freeze-thaw cycle. 20-foot seas are still hammering the coast. Black ice is spreading across untreated roads, and 2 more systems are already lining up to move over a snowpack that hasn't even stabilized. Meanwhile, the same atmospheric wave that buried Rhode Island pushed Oklahoma to 80 degrees with 10% humidity and critical fire danger in February, and there are still 552 active weather alerts across the country. The storm ended, but its consequences haven't even started. Tonight, we're breaking down why the next 72 hours may be more dangerous than the blizzard itself, and the pattern hiding underneath all of it that almost no one is talking about. If this story pulled you in, make sure you're subscribed so you don't miss what unfolds next, because we're not done with this pattern yet. Let me know in the comments where you're watching from and what conditions look like on the ground for you. And if you want to help the Skylab grow, share this one. You're the reason we get to ask the questions no one else does and keep following the threads others move past. So let's go back a little. Just hours after it stopped snowing on February 23rd, the news cycle did what it always does. It moved on. Damage totals, dramatic footage, a few feel-good stories about neighbors shoveling each other out, and then the chyrons shifted to something else. But here's what didn't happen. The National Weather Service didn't move on. And when forecasters who write technical documents for other meteorologists, not for cameras, not for clicks, when those people use the word historical, that's the moment you should stop scrolling and start paying attention. The area forecast discussion is not a press release. It's not written for you. It's written by meteorologists for meteorologists, a technical back channel where the people responsible for keeping you alive talk to each other in plain professional language with no incentive to dramatize anything. And in that document, issued after the snow had already stopped, they used the word historical, not significant, not impactful. Historical. That word has weight. That word means we are watching something that will be used as a reference point for decades. So what exactly are they watching? Let's start with the numbers, because the numbers are genuinely staggering. 2 to 3 feet of snow across Rhode Island and southeastern Massachusetts. 18 to 30 inches across the broader New York region, per the National Weather Service New York. Wind gusts of 60 to 80 miles per hour on Cape Cod, a range that sits squarely in Category 1 hurricane-equivalent territory. Just wind, just gusts, on a coastline that was already saturated from prior storm cycles. And when you layer that kind of wind energy onto 2 to 3 feet of fresh snowpack, what you get is not a blizzard. What you get is a restructured surface environment that will be actively dangerous for days after the last flake falls. Here's the number that most people missed entirely: 552. That's the number of active National Weather Service alerts that were still in place as of the day after the storm. 552. And here's the part that should make you pause. That number was nearly unchanged from the peak of the storm itself. Think about what that means. The storm, by every visual indicator, was over. Skies were beginning to clear. Satellite imagery showed the low pulling away, the classic signature of a departing system. And yet the alert footprint hadn't collapsed. It had barely moved. That's not a coincidence. That is a measurable, objective signal that the hazard did not end when the snowfall did. And there's a reason for that, a physical reason that most coverage completely ignores. In the final hours of this system, as the low-pressure center was already exiting the region, meteorologists observed something called mesoscale band regeneration, meaning the storm, even as it was technically departing, was still organizing, still producing structured precipitation bands. A system that continues to generate internal organization while pulling away is not a system that has released its energy. It's a system that has transferred that energy into the snowpack, into the ocean, into the cold dome sitting over the entire Northeast like a lid that won't come off. And this is the idea that is going to drive everything you're about to hear, so I want to plant it right now. This blizzard did not end. It transformed. The meteorological event, the low-pressure system, the active snowfall, the peak winds, yes, that phase concluded. But the atmospheric and surface conditions it created are now operating as independent hazard systems. The snowpack isn't just sitting there waiting to melt. The ocean isn't just calming down. The cold air isn't just slowly retreating. Each of these is an active participant in what comes next. And what comes next, in the next 72 hours, may statistically be more dangerous than anything that happened during the storm itself. That's not a dramatic exaggeration. That's what the data from prior major East Coast blizzards consistently shows. And the forecasters who write documents for each other, not for you, not for ratings, they know it too. Clear skies and a pretty sunrise do not mean the emergency is over. Sometimes they mean it's just getting started. So the question isn't whether this storm was historical. It clearly was. The question is, what does historical actually look like in the 72 hours after the snow stops? Because that's the part the news cameras have already left behind. Here is something that almost nobody talks about after a major snowfall. The snow doesn't just sit there, it does something. It participates. 2 to 3 feet of fresh snowpack covering the entire northeast is not a passive object waiting to be ploughed or shoveled or melted away by warmer temperatures. It is an active component of the regional atmosphere, and over the next several days it is going to do things to the air above it, the ground beneath it, and the infrastructure embedded in it that will make the post-storm period genuinely more treacherous than the storm itself. Start with something called albedo feedback. Albedo is simply the reflectivity of a surface, how much incoming solar radiation it bounces back rather than absorbs. Fresh snow has an albedo of roughly 80 to 90%, meaning nearly all of the sunlight hitting it gets reflected back into the atmosphere rather than absorbed as heat. Compare that to bare ground or asphalt, which absorbs the majority of incoming solar energy, and you start to understand what a 2 to 3 foot snowpack actually does to the temperature profile of the boundary layer, the thin slice of atmosphere right at the surface where you live and drive and breathe. The snowpack is actively maintaining cold. It is suppressing daytime warming. It is keeping the surface colder than it would otherwise be, longer than it would otherwise stay that way. And that matters enormously for what happens next. Because during the day, even under that suppressed warming, marginal melt begins. The sun angle in late February is high enough, the solar input strong enough that the very top layer of that snowpack starts to go through a phase transition. It doesn't fully melt, but it softens. It gets wet. Water migrates downward through the snow column. And then night comes, temperatures crash back below freezing, and that wet surface layer, the road, the sidewalk, the roof, refreezes. Not as fluffy snow, as ice. And this cycle, repeated over day 2, day 3, day 4 after a major snowfall event, is one of the most reliably dangerous atmospheric processes we know of. Not because it's dramatic, because it's invisible. This is why black ice doesn't peak on day 1 after a blizzard. It peaks on day 2 and day 3 when the freeze-thaw cycle has had time to work. On day 1, roads are covered in snow. Everyone can see it. Everyone adjusts. By day 3, there's a thin, transparent glaze on every road that wasn't treated perfectly. And the headlines have moved on, and people have stopped thinking of themselves as storm survivors and started thinking of themselves as people running errands again. That's when the accident rates spike. That's when the emergency room starts seeing the second wave of storm-related injuries. Not from the storm, from the aftermath. The same process is happening to your roof right now. If you're in the affected zone, a heavy snowpack doesn't apply uniform load. As the surface melts and refreezes, load redistribution occurs. Wet snow is significantly denser than dry snow, sometimes 3 to 5 times denser by weight per cubic foot. As that top layer transitions through freeze-thaw cycles, the effective weight on your roof structure changes. It shifts. And structural engineers will tell you that it's often not the peak load that causes failure, it's the cycling, the repeated stress. The microfracturing. Roofs that held through the actual storm sometimes fail on day 3 or day 4, when the snow is visually diminishing but the internal structural stress has been accumulating for 72 hours. The same physics is attacking every road surface in the region. Asphalt is a flexible composite material, and it handles stress relatively well until water gets into its microfractures, freezes, expands, and then thaws. Each expansion cycle widens those fractures slightly. Each refreeze deepens them. After a series of freeze-thaw cycles following a major snow event, asphalt that appeared intact can shatter into pothole fields within days. Transportation departments in the northeast know this pattern well. The pothole season isn't during the storm. It's 3 to 10 days after the storm when the roads look fine but are structurally compromised at the micro level. And then there's something even more counterintuitive: wind-driven sublimation. Even in clear, cold weather with no new precipitation, the existing snowpack continues to lose mass through sublimation, direct conversion from solid to vapor, and through wind transport. Gusty post-storm winds pick up loose surface snow and redistribute it. Roads that were ploughed clean can accumulate new drifts in hours with no new storm required. This happens in clear weather, under blue skies with no precipitation anywhere on radar. And because it looks calm outside, most people don't account for it. All of this, the albedo maintenance of the cold dome, the freeze-thaw cycling, the load redistribution, the sublimation drifting, is happening right now across the entire northeast snowpack. And here is the piece that directly connects to what's coming in the next 48 hours. That snowpack is cold preserving the atmosphere above it in a way that will directly influence how the next two incoming weather systems behave when they arrive. The snow that fell on February 23rd is not just an aftermath problem. It is actively shaping the next storm. The surface has been changed, and any system that moves across that changed surface is going to behave differently than it would have a week ago. The storm transformed the environment, and the environment is now transforming what comes next. While the interior of the northeast is dealing with frozen roads and stressed rooftops, something equally serious and far less visible is unfolding offshore. Confirmed wave heights of 20 feet were recorded off eastern Massachusetts in the immediate post-storm period. 20 feet. That's not a number to skim past. That's a 4-story building of organized water moving toward a coastline. But here is the part that actually matters for understanding why the coast is still in storm mode even after the system departed. The wave period. Wave period is the time between successive wave crests passing a fixed point. Short period waves, 4, 5, 6 seconds, are wind chop. They're chaotic, disorganized, and they dissipate relatively quickly once the wind that generated them stops blowing. But the waves recorded off eastern Massachusetts had periods of 13 seconds. 13 seconds between crests. That is organized swell. That is energy that has been transferred from the atmosphere into the ocean at depth, structured into coherent wave trains that carry their momentum across hundreds of miles with minimal energy loss. Wind chop is a ripple on the surface. 13-second swell is a freight train running at depth. And here is what that means for the coastline. The storm's peak winds may have passed, but the ocean's energetic response to those winds has not. The ocean has a memory. Energy imparted to it during the storm's peak doesn't simply stop when the atmospheric forcing does. It propagates, it travels. And it arrives at the coastline on its own schedule, which is often 12 to 36 hours behind the storm's meteorological peak. This is why coastal erosion frequently maximizes after a storm center has already departed. The most destructive wave energy reaches the shore after the cameras have left. Add to that a residual storm surge of 1 to 1.5 feet that was still stacking against the coast in the post-storm period. Surge is not just about water height in the dramatic sense of water flowing into streets. Even a foot of residual surge, stacked against astronomical high tide timing, repositions the wave run-up zone significantly higher on the beach face. And when 13-second swell is arriving at the same moment that residual surge has elevated the baseline water level, wave energy is reaching infrastructure, seawalls, jetties, dune faces, coastal roads, that it normally wouldn't touch. Seawalls are not infinitely durable objects. They are engineered to absorb a certain number of high-energy wave impacts before their mortar joints begin to fail, before their foundations scour deepens, before the differential pressure on their landward and seaward faces begins to crack the structure itself. A single major storm event can bring a seawall to 90% of its structural tolerance. The post-storm swell period, the repetitive 13-second impacts continuing over multiple high-tide cycles, can push it past that threshold quietly, with no single dramatic moment. Weeks later, a coastal engineer does an assessment and finds failure. Nobody televised it, nobody connected it to the blizzard, but the physics ran in a straight line from February 23rd to that crack in the foundation. This is what the ocean's kinetic memory means in practical terms. The energy isn't gone. It's just moving slower than the news cycle. And because the damage it produces tends to be cumulative rather than cinematic, no footage of water flooding a parking lot. Just a seawall that's a little shorter than it was, a dune face that's a few feet narrower, a coastal road undercut in a way that won't be obvious until a truck drives over it. It rarely makes the post-storm coverage. The coast is not recovering. It is still absorbing, and it will continue absorbing wave energy through multiple tidal cycles, while the interior northeast simultaneously deals with its own freeze-thaw hazard phase. Two different physical systems, both still active, both still dangerous, both operating on timescales the news cycle isn't built to track. And here's where it gets even more complicated, because while the ocean is still processing the energy from the storm that just ended, two more atmospheric systems are already approaching the region. And they're approaching a surface environment that has been fundamentally altered. Not the same northeast as 2 weeks ago, a colder, icier, structurally stressed northeast, one where the margin for error on the next forecast is razor thin. The first system is a clipper, a fast-moving Alberta-origin low-pressure system that sweeps across the Great Lakes and into the northeast, bringing light to moderate precipitation. On its own, in normal conditions, a clipper is a minor event. An inch or two of snow, some gusty winds, an inconvenience. Meteorologists forecast these regularly and the public barely notices. But Wednesday's clipper is not arriving into normal conditions. It's arriving into a surface environment with 2 to 3 feet of existing snowpack, a hard frozen road network, and a cold dome sitting over the entire region that is suppressing boundary layer temperatures well below seasonal norms. In that context, even a light precipitation event becomes something different. Fresh snowfall on top of an existing ice-over-snow surface reduces friction to near zero on untreated roads. A half inch of new snow on black ice is in many ways more dangerous than 6 inches of fresh snow on a dry road, because the fresh snow signals danger visually while the thin layer on black ice is nearly transparent. Drivers slow down for 6 inches. They don't always slow down for what looks like a dusting. But the clipper is not the system that's generating the most uncertainty in the forecast models. That distinction belongs to the Thursday low developing over the Ohio Valley, and the uncertainty around that system is genuinely significant. The core question is track. A track slightly farther north keeps cold air locked in place across the mid-Atlantic and southern New England, maintaining the frozen boundary layer and producing predominantly snow. A track slightly farther south allows warmer air to undercut from below more efficiently, raising surface temperatures into the critical transition zone, the zone where forecasters face the hardest possible call. That zone sits between roughly 30 and 34 degrees Fahrenheit at the surface. In that range, precipitation type becomes exquisitely sensitive to small temperature differences measured in tenths of a degree. Rain becomes freezing rain. Sleet and freezing rain mix in proportions that vary block by block. And the probabilities for freezing rain across western Maryland's cold pocket, a terrain-influenced area where cold air pools with particular stubbornness, were sitting at 30 to 60% as of the most recent model runs. 30 to 60%. That is not a confident forecast. That is a range that spans the difference between an inconvenience and a catastrophe. The primary model disagreement is timing. The faster solutions, models that move the Thursday system through more quickly, tend to produce a predominantly snow outcome because the cold dome doesn't have time to fully erode before precipitation onset. The slower solutions allow warmer air advection to work on the cold dome for additional hours before precipitation begins, nudging the surface temperature critical fractions of a degree higher and pushing the precipitation type toward freezing rain. A 2 to 4 hour difference in timing changes the impact category of this event entirely. And right now, the models don't agree on timing to within 2 to 4 hours. This is what forecasters mean when they talk about forecast fragility. Not that they're bad at their jobs, they are extraordinarily skilled at an extraordinarily difficult problem. It's that the physical system itself is operating at a point of sensitivity where small differences in initial conditions propagate into large differences in outcome. A butterfly effect that is real, measurable, and directly relevant to whether your power stays on Thursday night. Because the ice accretion thresholds for tree failure are not linear. A quarter inch of ice accretion on a branch already stressed by the weight of existing snow can be survived. A half inch often cannot. and power outage probability curves under ice loading are dramatically steeper than under equivalent snow loading, because ice is denser, adheres to power lines differently, and creates load distributions that snow does not. A quarter inch of freezing rain on a snow-loaded power grid is not a minor event. It's potentially the kind of event that takes utilities days or weeks to restore. The board has changed. The surface the Thursday system is approaching is not the surface it would have approached 2 weeks ago. And the cold dome that's still sitting over the region, maintained in part by that massive snowpack reflecting sunlight back to space, is the variable that determines whether Thursday's system is a footnote or a headline. And right now that determination hangs on hours, on tenths of degrees, on whether a low tracks across one county or the next county south. There's a concept in complex systems science called surface preconditioning. It refers to the way prior events alter the baseline state of a system, making it more or less vulnerable to subsequent stressors than it would otherwise be. In a meteorological context, surface preconditioning means that the northeast entering the next 48 hours is not the same northeast that entered February 23rd. The baseline has shifted. And when the baseline shifts, events that would ordinarily be manageable can become something else entirely. Consider the sequence that is currently unfolding. You start with a historic snowpack, 2 to 3 feet across a major populated corridor. On its own, that's a significant event, but it's the kind of event the region has infrastructure and protocols to handle. Then you apply a hard freeze cycle, temperatures dropping well below freezing overnight, locking that snowpack into ice, creating the black ice conditions on every untreated surface. Still manageable in isolation. Transportation departments salt, sand, and plow. Emergency services go on heightened alert. It's a known protocol. Then the clipper arrives and deposits a fresh inch or two of snow on top of the existing ice over snow surface. Still in isolation, a minor event. But now you're not dealing with a fresh snow event on a dry road. You're dealing with fresh snow on a frozen, ice-underlain surface where traction is already compromised, and where the marginal temperature range means that fresh snow is occasionally falling as sleet, creating a bonded layer that plows can't easily remove. The compound is now harder to manage than either component alone. And then the Thursday system arrives into this preconditioned surface, freezing rain potential, ice on snow loading, and an infrastructure network, roads, power lines, trees, rooftops that has already been stressed for 4 to 5 days continuously. This is the stacking effect. And the reason it matters is that the risk doesn't add linearly. Each additional stressor on a preconditioned system produces a disproportionate impact relative to what that stressor would cause in isolation. Structural engineers call this fatigue loading. Emergency managers call it compound event risk. Actuaries, who are perhaps the least dramatic people on Earth, call it the part of the distribution that breaks their models, because standard risk calculations assume independence between events. They assume each event starts fresh. When events compound on preconditioned surfaces, independence fails, and the tail risks become much heavier than any single event model predicts. We see this pattern in the data from prior major East Coast blizzard sequences. Emergency room visits don't peak during the storm, they peak on day 2 and day 3, when the freeze-thaw cycle has created invisible ice, when the complacency has set in, when people are moving at normal speeds in conditions that demand they don't. Vehicle accident rates show the same pattern, a secondary spike on days 2 through 4 that often exceeds the initial storm period spike. Insurance claim timelines tell the same story, a clustering of new claims starting 48 to 72 hours after the storm's meteorological conclusion, representing roof failures, infrastructure damage, vehicle accidents, and property losses that the initial storm coverage never captures. There's also a psychological component to this, and it's worth naming directly. Once the dramatic imagery fades, once the footage of cars buried in snow and coastal flooding gives way to clear skies and plow trucks working normally, there is a measurable cognitive shift in how people assess their risk environment. They stop thinking of themselves as people in a post-storm hazard zone and start thinking of themselves as people whose storm is over. And that cognitive shift happens before the physical hazard has actually resolved, before the ice has finished forming, before the trees have reached their breaking point, before the next system has arrived. Think of it as the meteorological equivalent of a wildfire aftermath. The fire is out, but the hillsides are stripped of vegetation, the soil is hydrophobic from heat, and the first rain event triggers debris flows that kill more people than the fire itself. The primary disaster preconditions the surface. The secondary event, which would have been survivable in isolation, becomes catastrophic. The West Coast has learned this lesson in fire. The Northeast is being reminded of its version right now in ice. The aftermath risk may statistically exceed the peak storm risk. That is not a dramatic claim. That is what the compound event literature consistently shows. And yet the cameras are gone, the alerts are fading from public attention, and the preconditioned surface is sitting there, waiting for the clipper, waiting for Thursday, waiting for the freeze-thaw cycle to do what freeze-thaw cycles do. So let's ask the question that nobody in the post-storm coverage is actually asking. When does a storm end? Because the answer, it turns out, depends entirely on what you're measuring. And most of the things we use to tell the public a storm is over are the least meaningful metrics for actual hazard duration. The meteorological end of a storm is well defined. It's when the low-pressure system has departed, when active precipitation has ceased, when wind speeds have dropped below threshold criteria. By those measures, the February 23rd blizzard ended. Check. The news cycle's definition of storm end is even simpler: when the dramatic imagery stops, when the footage of snow falling and waves crashing is replaced by footage of plows and shovels. Check. That happened within hours of the meteorological conclusion. But there is a third definition, one that emergency managers and structural engineers and coastal scientists actually use, and it has nothing to do with when the snow stopped falling. It has to do with when the surface energy state of the affected region has normalized back to pre-storm baseline. And by that definition, this storm is nowhere near over. 552 active National Weather Service alerts, nearly unchanged from the storm's peak. That number is not a bureaucratic artifact. It reflects a physical reality. The hazard footprint, the geographic area where conditions exist that require official warnings to protect human life and property, has not contracted. The storm's alerting infrastructure is still fully deployed because the conditions that justify that deployment still exist. The cold dome sitting over the Northeast has a persistence forecast that runs through the end of the week. It will not simply erode when the sun comes out. It's being maintained by the albedo feedback of the snowpack it helped create, in a self-reinforcing loop that insulates it from the normal warming that would otherwise begin dissipating it. The marine energy, 20-foot seas, 13-second wave periods, has its own dissipation timeline measured in days, not hours, running through multiple tidal cycles and continuing to stress coastal infrastructure that has already absorbed peak storm loading. Infrastructure stabilization, the point at which roads, bridges, power systems and structural components have either failed or adjusted to their new load conditions, typically lags the meteorological storm by 3 to 7 days in a major event. We know this from prior storms. We know it from insurance claim data, from utility restoration timelines, from coastal survey assessments that consistently find damage occurring and progressing for days after the storm that caused it has been forgotten by everyone except the people filing claims. There's a useful term for this phase, the structural phase of a storm's life cycle. It's the period after the meteorological event has concluded, during which the altered surface environment continues to produce hazardous conditions, compound stressors, and infrastructure failure, often with no new weather event required to trigger it. Just the ongoing physics of the changed environment doing what physics does. Storms are remembered for their snowfall totals, their peak wind gusts, their dramatic surge imagery, almost never for their structural phases. And yet the structural phase is where a significant portion of the actual damage, injury, and economic impact accumulates. We have systematically undermeasured the full duration of major storm events because we've been using the wrong stopwatch. This blizzard's structural phase is active, and it's about to receive 2 new meteorological inputs, the Clipper and the Thursday Low, on top of a surface environment already in the middle of its most dangerous period. Which raises a larger question: is this a regional meteorological story, Or is something bigger happening? Because the same atmospheric pattern that buried the northeast under 3 feet of snow has been doing other things simultaneously. Things that, when you lay them out side by side, start to look less like a collection of separate weather events and more like one connected, continental-scale expression of something we should probably understand better. While emergency managers in Rhode Island were counting snowfall in feet, something remarkable was happening simultaneously about 1,500 miles to the southwest. Oklahoma, on the same day the Northeast was under blizzard conditions, was recording temperatures near 80 degrees Fahrenheit with relative humidity around 10%. 10%. That is desert-level dryness in February in Oklahoma. And the Storm Prediction Center, the same federal agency that issues tornado watches in spring, had issued a critical fire weather outlook for the region, meaning conditions were favorable for rapid, uncontrolled wildfire spread across the southern plains. That is not a separate story. That is the same story. Both of those events, the blizzard burying New England and the extreme fire weather scorching the southern plains, were produced by the same atmospheric feature, a highly amplified Rossby wave pattern embedded in the upper-level flow of the northern hemisphere. Rossby waves are planetary-scale undulations in the jet stream, the high-altitude river of fast-moving air that separates cold polar air from warmer subtropical air. In a low-amplitude pattern, the jet stream runs relatively straight from west to east, and weather systems are moderate and relatively short-lived. But when the jet stream becomes highly amplified, when its troughs plunge deep toward the equator, and its ridges build high toward the poles, the temperature and moisture contrasts on either side of it become extreme, and they persist far longer than normal. The same ridge-trough pattern that drove Arctic air southward into the northeast, producing the conditions for a historic blizzard, simultaneously drove abnormally warm air northward into the Central Plains, compressing it, drying it, and delivering it to Oklahoma at temperatures and humidity levels that belong in August, not February. The geographic contrast is staggering: 80 degrees and fire danger a day's drive from 2 feet of snow and coastal flooding. But atmospherically, they are not contrasts, they are both consequences of the same amplified wave. 2 sides of the same feature, and it didn't stop there. The same Rossby wave pattern produced wind gusts exceeding 100 miles per hour along the Rocky Mountain front, the kind of downslope windstorm that is itself a significant life safety event, capable of destroying structures and driving catastrophic wildfire spread. It produced freeze warnings extending into Florida, where temperatures dropped to levels that threaten sensitive agriculture and can cause significant economic damage to crops that have no tolerance for sustained freezing. In total, a single amplified wave pattern simultaneously generated a historic northeast blizzard, critical fire conditions in the south-central states, extreme mountain winds, and frost damage threats in subtropical Florida. This is what meteorologists mean when they discuss meridional transport, the north-south movement of air masses driven by an amplified meridional jet stream pattern, rather than the more common zonal or east-west flow. In a highly meridional pattern, the atmosphere is essentially running parallel to the lines of longitude rather than the lines of latitude, moving extreme cold far south and extreme warmth far north simultaneously, creating the kind of sharp contrasts that produce the most intense individual weather events. Now here is the connection back to the central thread, because this is not just geographical trivia. The amplified Rossby wave pattern that produced the February 23rd blizzard has not dissipated. It is still active. The same upper-level feature that drove the storm into the northeast is the same feature that is now steering the Clipper and the Thursday Ohio Valley low toward a preconditioned, snowpack-covered northeast surface. The system that generated the initial event is still operating. The atmospheric forcing has not relaxed. And as long as that wave pattern remains amplified, new weather systems will continue to be generated, steered, and intensified by its same dynamics. There is an important scientific caveat here, and I want to state it clearly. Whether Rossby wave amplitudes are increasing on a climatological basis, whether highly meridional, high-amplitude patterns are becoming more frequent or more persistent than they were in prior decades, is genuinely unsettled science. Research exists that suggests a statistical connection between Arctic warming, reduced equator-to-pole temperature gradients, and increased jet stream waviness. That research is real, and it's published in peer-reviewed journals by serious scientists, but it is also contested. Other researchers find the statistical signal weak, the attribution uncertain, the natural variability of jet stream behavior large enough to make trend detection difficult. I'm not going to tell you that climate change caused this blizzard, or that amplified Rossby waves are definitively becoming more common. What I will tell you is that the pattern that produced this event is a real, documented atmospheric phenomenon, that it simultaneously generated extreme conditions across the continent, and that it has not yet relaxed. The board hasn't just been changed in the northeast, the entire continental board has been altered. And while the blizzard's aftermath compounds on the surface below, the wave pattern above is still writing the next chapter. On the same day the northeast was being buried under 3 feet of snow, something was happening 93 million miles away that had nothing to do with the blizzard, and yet managed to arrive at Earth's doorstep at almost exactly the same moment. A coronal hole on the sun's surface, a region of open magnetic field lines where the sun's outer atmosphere vents directly into space, had been rotating into a geo-effective position for several days. And on February 23rd, the high-speed solar wind stream it produced arrived at Earth, driving a G1 geomagnetic storm. G1 is the lowest level on the NOAA geomagnetic storm scale. It's not a civilization-ending event, but the associated solar wind speed peaked around 768 kilometers per second, nearly 2.5 times the nominal solar wind speed, and electron flux levels in the radiation belts approached 5,000 particle flux units, which is within the range that triggers satellite charging alerts from space weather operations centers. For satellite operators, for GPS system administrators, for HF radio users, G1 events are operational. They are real and they are managed. What makes this particular event interesting is the solar context. The sun was visually spotless, no sunspots visible on the disk. This is somewhat unusual for a geomagnetic storm event, because most people associate geomagnetic storms with solar flares and coronal mass ejections, which require active sunspot regions to generate. But this storm was coronal hole driven. The solar cycle we are currently in, solar cycle 25, is in its declining phase from solar maximum, and during the declining phase, recurrent high-speed streams from long-lived coronal holes become the dominant source of geomagnetic activity. The sun doesn't need to be dramatic to be active. A quiet-looking sun with an open magnetic corridor can deliver a sustained geomagnetic disturbance just as reliably as a flare-active sun. Now, and I want to be very clear about this, there is no proven physical mechanism by which a G1 geomagnetic storm influences tropospheric weather. The energy deposited into the upper atmosphere by geomagnetic storms is real, measurable and significant at ionospheric and magnetospheric altitudes. But the troposphere, the bottom layer of the atmosphere where weather happens, where you live, where blizzards form, is shielded from direct electromagnetic effects by the massive atmosphere above it. The blizzard was not caused by the geomagnetic storm. The amplified Rossby wave pattern was not triggered by the coronal hole. That needs to be stated plainly. There are, however, weak statistical correlations in the scientific literature between high-speed solar wind streams and certain parameters of the northern annular mode and the North Atlantic oscillation, atmospheric circulation patterns that influence the kind of amplified wave pattern we've been discussing. These correlations are small, they are disputed, and researchers who study them are careful to describe them as potential statistical associations rather than causal relationships. A correlation in atmospheric data is not a mechanism. And without a mechanism, claiming causation is scientifically irresponsible, so I won't do that. What I will say is this: the psychological experience of living through a week where a historic blizzard, continental-scale fire danger, extreme mountain winds, and a geomagnetic storm all arrive simultaneously is the experience of convergence, of multiple systems appearing to move together even when the physics says they're independent. And that convergence experience is real, even when the convergence isn't. Because our pattern recognition systems, the ones evolution built into us to detect predators and interpret environmental signals, are exquisitely sensitive to clustering. We are built to see patterns. We sometimes see them where they don't exist. But we also sometimes see them where they do. The geomagnetic storm did not cause the blizzard. But both events exist within the same week, on the same planet, in the same converging information environment, and together they contribute to the same perception of a world running hotter, more energetically, more simultaneously extreme than the one we were told to expect. Whether that perception reflects a statistical reality or a pattern recognition artifact is, Honestly, one of the more interesting questions you could ask right now. What is not a perception artifact is the snowpack, the ice, the wave energy, the cold dome, the incoming systems. Those are as real as anything gets. The human brain is a pattern recognition machine, and it was not designed for a world where 552 weather alerts appear on a single dashboard in real time. For most of human history, if you experienced a blizzard, you experienced a blizzard. You didn't simultaneously know that Oklahoma was on fire, that solar wind was hitting Earth's magnetosphere, that wave heights off the coast were still 20 feet. That convergence of information is new. The events themselves are not necessarily more frequent or more extreme than prior decades, though some of them clearly are. But our ability to see them all at once, stacked and simultaneous on a real-time dashboard, is entirely new. 552 active alerts is an enormous visual reinforcement of crisis. It's the kind of number that produces a felt sense of systemic breakdown, even if each individual alert is a routine, properly calibrated operational output from a forecaster doing their job well. Seeing all 552 simultaneously, which is possible now in a way it wasn't 20 years ago, can generate a perception of catastrophe that may or may not match the physical reality on the ground. And it can also paradoxically produce the opposite effect: alert fatigue. A normalization of emergency, a sense that the warnings have become so constant that they've lost their signal value. Both effects are real. Both are worth being aware of. The difference between clustering and causation is one of the most important cognitive distinctions in science, and it's one that real-time data environments make harder, not easier, to maintain. In a world without instant data aggregation, the Oklahoma fire weather and the Northeast blizzard would have felt like separate events in separate news cycles. Today they feel like chapters in the same story. And the feeling isn't entirely wrong, they do share a common atmospheric cause, but the temptation to extend that connection further than the physics actually supports is real and worth resisting. Here's what I want you to take from this. The compounding on the ground in the Northeast is not a perception artifact. It is measurable, operational, physical. The freeze-thaw cycling is real. The wave energy is real. The cold dome is real. The stacking risk from incoming systems is real. The 552 alerts reflect a real, persistent hazard footprint. The convergence you're feeling may be partly a product of information density and pattern recognition, but the danger it's pointing at is entirely genuine. Let's map what the next 72 hours actually looks like, not as a dramatic scenario, but as a risk curve built from what prior major storm sequences have consistently shown. Day 1 of the post-storm period is dominated by the refreeze. Every surface that experienced marginal daytime melt during the first clear post-storm day is now a glazed, invisible ice surface. Commuter traffic spikes on day 1, people returning to work, reopening their routines, moving at speeds and with confidence levels that don't match the road conditions beneath them. Emergency departments historically see the first post-storm surge of fall injuries, vehicle accidents, and cold exposure cases on day 1. Not during the storm when people stay home, afterward, when they don't. The risk is high, the visibility of that risk is low. That combination is the definition of a dangerous operational environment. Day 2 brings the Clipper overlay. Fresh precipitation, probably light, possibly mixed, arriving onto a surface already compromised by the freeze-thaw cycle. The new snow on black ice scenario that I described earlier. Transportation departments are stretched thin. Their equipment and personnel have been running continuously since before the original storm made landfall. Fatigue in the operational response system mirrors the fatigue in the physical infrastructure. Decision-making slows. Resources that would normally be pre-positioned are now being managed reactively. Insurance claim volume begins accelerating on day 2, not from dramatic single-event losses, but from the accumulation of smaller incidents multiplying across a stressed population. Day 3 is where the models diverge and where the uncertainty is highest, because day 3 is when the Thursday Ohio Valley low arrives, or when its leading edge of freezing rain potential arrives into a surface that has now been continuously preconditioned for 72 hours. Roof structures have been through 3 complete freeze-thaw cycles. Power lines have been under variable ice and snow loading for 3 days. Trees, particularly hardwoods with leaves gone but still carrying accumulated ice and snow on their branches and bark, are operating at load fractions that would surprise most homeowners who walk under them without looking up. Power outage events triggered by ice loading on day 3 of a storm sequence have historically been among the most geographically widespread outages in the Northeast's utility history, because they affect infrastructure that appears to have survived the storm but has been quietly accumulating structural deficit throughout the post-storm period. The cold dome's persistence forecast through the end of the week means that temperature recovery, the warming that would begin dissipating ice and reducing freeze-thaw intensity, is delayed. Model agreement on temperature stagnation across the region is relatively high, which is the one part of this forecast that isn't fragile. It's going to stay cold, which means the ice isn't going anywhere, which means every new precipitation input, Clipper, Ohio Valley Low, or anything that forms in between arrives onto a surface that cannot drain, cannot absorb, cannot warm its way out of the problem. The risk curve over the next 72 hours does not decline. It remains elevated, and depending on the Thursday system's track and timing, it may spike significantly on day 3. This is not the tail end of a storm event. This is the middle of a compound hazard sequence, and the people most at risk during this period are the ones who have already decided the storm is behind them. There's a particular kind of damage that storms leave behind that almost never makes the news. It doesn't happen with a crash or a flood surge. It happens quietly, over days in structures that appear intact, and it is responsible for a significant share of the total economic and human cost of major winter storms, a share that is systematically undercounted because it occurs after the cameras leave. Roof collapses are the most dramatic expression of this structural lag. The physics are straightforward. A heavy snowpack applies downward load to a roof structure that was engineered for a specific maximum load distribution. During the storm, peak load is reached and either the structure holds or it fails immediately. Most hold. But then the freeze-thaw cycle begins. The snowpack partially melts and refreezes, increasing density. Load distribution shifts as wet snow slides and redistributes across the roof surface. Ice dams form at the roof's cold edge, ridges of ice that trap meltwater and allow it to back up under shingles and into the building envelope. And the structure, which held fine through the storm, begins accumulating damage it doesn't show on its exterior. The majority of documented roof collapses following major snowstorms occur between 48 and 96 hours after the storm's meteorological conclusion. Not during, after. And they tend to cluster on structures that were already carrying deferred maintenance. Older buildings, agricultural structures, commercial buildings with flat or low-slope roofs that aren't designed for the kind of wet, dense snow load that a freeze-thaw cycle produces. Ice dam formation is slightly more democratic. It affects well-maintained modern homes almost as readily as older structures, because ice dams are a function of thermal gradient, not structural quality. A warm living space below a cold roof surface creates the conditions for melt at the roof deck and refreeze at the cold overhang, regardless of how new the shingles are. And the water intrusion from ice dams, which can begin within 24 to 36 hours of the post-storm refreeze, causes damage that homeowners often don't discover for days or weeks, when staining appears on interior ceilings or walls boo from moisture absorption. Tree failure is another structural lag phenomenon that deserves specific attention. Large hardwood trees in the Northeast have been carrying compounded ice and snow loads for 72 plus hours by the time the Thursday system arrives. The failure threshold for ice-loaded branches is sensitive to the specific species, prior health, and the rate at which additional ice accretes. A branch that has been surviving its current load for 2 days can fail suddenly when an additional quarter inch of ice accretion from a freezing rain event shifts the load-to-strength ratio past the breaking point. Utility companies know this pattern well. It's why ice storms cause more widespread and longer duration power outages than snowstorms of equivalent precipitation volume. Ice accretes directly to power lines and tree limbs in a way that snow does not, and it fails structures that have already survived peak loading during the main event. Municipal systems are operating in their own structural lag phase. Road treatment budgets, salt stockpiles, plow equipment maintenance schedules, and crew rest requirements all reflect a storm system that began before February 23rd and has been running continuously. The Thursday system, whatever it ultimately delivers, arrives into a municipal response posture that is already significantly depleted from its pre-storm baseline. Slower response times, stretched resources, delayed treatment applications. which means road conditions during the Thursday event will be worse than they would have been had the event occurred independently. None of this will be on the evening news. Structural lag events don't produce footage. They produce claims adjusters, insurance tallies, and local news briefs about a building that came down on a Thursday afternoon, with no storm currently falling. But the storm wrote that chapter. It just wrote it slowly enough that the cameras missed it. We started with the word historical. Let's end with a question. The February 23rd blizzard ended meteorologically. The low departed, the snowfall stopped. By the conventional metrics we use to define storm duration, it's over. But we've spent this entire analysis showing that over is the wrong word for what's actually happening. That the hazard phase is not only continuing, but potentially intensifying. That the surface environment has been fundamentally altered. That two more atmospheric systems are approaching it. That the structural lag is only beginning. And that the compound risk over the next 72 hours may statistically exceed anything that happened during the storm itself. 552 alerts still active. A cold dome still in place, 20-foot seas still impacting coastlines, freeze-thaw cycling still operating on every road surface and roof in the region, a clipper inbound, an Ohio Valley low, uncertain in track, fragile in forecast, potentially devastating in impact. And a Rossby wave pattern, still amplified, still steering systems, still generating the continental scale extremes that put Oklahoma at 80 degrees and Rhode Island under 3 feet of snow in the same 24 hours. This is what a compound hazard sequence looks like from the inside. Not one dramatic event with a clear endpoint. A cascading series of interacting stressors, each one making the next more consequential, each one arriving into a surface environment that the previous one has already degraded. And the thing that makes this particular sequence worth examining carefully is the question it raises about whether this type of compounding is becoming more common. I want to be honest about the limits of what we know here. Whether the frequency or intensity of post-storm compound hazard sequences is increasing is a genuinely difficult empirical question. Storm occurrence data goes back far enough to detect some trends, but compound event data, the specific intersection of primary storm events with secondary freeze-thaw hazard phases, with post-storm marine energy persistence, with subsequent incoming systems stacking onto preconditioned surfaces, that kind of compound event analysis is a younger field, and the statistical record is shorter. We can identify individual historical analogues. We can note that the conditions for compounding seem to be present. What we cannot say with confidence is whether the pattern is changing, and if so, whether that change reflects natural variability or a shift in underlying climate state. What we can say is this: the tools for measuring and communicating compound hazard persistence are not yet keeping pace with the actual risk. We measure storm intensity at peak. We report storm duration through the meteorological lens. We end our coverage when the cameras stop finding dramatic footage. And in doing so, we systematically undercount the danger that accumulates in the structural phase, in the freeze-thaw cycles, the offshore wave energy, the ice dam formation, the loaded trees and power lines, the preconditioned roads awaiting the next half inch of freezing rain. The blizzard of February 23rd was historical. The word the forecasters chose matters. But what may matter even more in terms of preparing for the next one, and the one after that, is building an understanding of storms that doesn't end when the snow stops falling. Because the snow stopped falling. And the hazard didn't. The next 72 hours will tell us how bad this structural phase gets. The answer to the broader question whether compounding is the new extreme may take much longer to know. But the question itself is one we should probably stop ignoring. The storm transformed. Are we paying attention to what it became?